Writing asynchronous code is a complicated endeavor, to say the least. And it doesn't help that there's so many misconceptions around this topic. What does asynchronous mean in the first place? And how is it different from concurrent or parallel? Some people seem to be using these terms interchangeably, which only helps feed into the confusion that new programmers have around this topic. In the past few weeks, I looked into lots of tutorials and best practices on this topic. And this video is the essence, or rather the consensus I could take away from that material. Part of this is going to be on the general concepts of async code execution, but as usual, we are also going hands-on with Rust. So lean back, prepare a cup of your favorite coffee, a cup of your favorite green tea, and let's learn together. I think it would be a great idea to first clarify some of the terms. Let's start with synchronous execution. A task is a sequence of operations. Think of it, for example, as a function. And I've outlined this task on a timeline. The task is usually executed from start to finish because this is a synchronous task. And actually, synchronous execution is the default operation mode of every program that you would usually write. Now, let's get into asynchronous execution. Asynchronous execution happens when a task is executed, but there are some breaks in between. And those breaks are usually due to waiting for something else. And a very common reason to wait would be file I/O, or it would be waiting for a network request. And you can see that task 1 starts off until there is a time where task 1 needs to wait for something. And during this time, task 2 can start execution. Note that while task 2 is executing, task 1 is in a break. And now whenever task 2 hits a reason to break or to wait for something else, then task 1, for example, could continue execution. So this allows us to jump between execution of totally unrelated functions. So we're not talking about task 1 is calling task 2 and then task 2 is finished and it gives back control to task 1. But we just have some reason to wait, and therefore a totally unrelated task, which is task 2, can then start execution. Now, what is parallelism? Parallelism is defined by two tasks running at the exact same time. Note that this does not have to mean that they start at the same time or that they finish at the same time, but only that there is one moment in time where both of them are actually running at the same time. And you can see here in the example, task 1 starts way ahead of time, but while task 1 is running, task 2 has started and they are now running at the exact same time. And those tasks can be either independent or they can communicate. And the execution of the code inside each of the tasks can be synchronous. Now, let us define concurrency. A definition that I find very helpful is that in a concurrent environment, a second task is started before another task, in this case task 1, has ever finished. And if you paid close attention, you will have noted that both parallel execution and asynchronous execution fit this definition of concurrency. And this is why concurrency is the bigger term that contains both parallel and asynchronous execution. As always, I'm trying to make these tutorials as hands-on as can be. So therefore, let's just start to implement an async function in Rust. The first thing we need to know is the async keyword. So if we have a function that is called foo, which returns u32, it's gonna print line in foo, and then return 5. We can make this an async function by just slapping the async keyword in front of it. And this is part of the core language in Rust. Now let's see what happens if we call this function. Actually, nothing happens. We don't get this print line in foo anywhere. Instead, we get a warning. Unused implementer of future that must be used. Note, futures do nothing unless you .await or poll them. So what are exactly futures? Maybe we can find out more about it if we just save the return type of this function. And because we see the type now, we see that we get something that implements future and has an output of u32. Well, a future is a promise that whenever this function is actually being executed, it will eventually return a U32 to us. This is what the output stands for. However, as the compiler already said, futures do nothing unless you .await or you poll them. Well, the Rust compiler is always very helpful, so let's just .await it. The problem is now that await is only allowed inside asynchronous functions and blocks, which means only if you are in an asynchronous function, you can execute an await statement. So no problem, we'll just put the async in front of the main. Wait, main function is also not allowed to be async. Well, too bad. How are we ever gonna start an asynchronous function? Well, for this, I think we first have to understand more about how asynchronous code is executed in the first place. I think we need to go to the very basics and how our computer operates and how it executes the code that we want it to execute. The first thing we need to understand is a thread. A thread is a process that can execute code. And the important thing to note is that threads are managed and created by our operating system. And those threads are then scheduled for execution on our CPU cores. So if we have more threads than we have cores, some of the threads will have to wait until there is space on the cores to run them. Threads can be spawned with did-thread spawn in Rust. And if you haven't heard about that, then go watch my video on it and you'll be up and running in no time. With threads, we can achieve parallel execution. In this example, we have two threads. Each of the threads only has one task, which can then run synchronously on the threads. But if both threads are scheduled for execution at the same time on distinct cores, we have what is actually parallel execution. The problem is switching between the threads is very, very expensive because each of the thread has its own stack. And whenever a thread is put to sleep, this stack is stored somewhere in memory. And whenever the thread is being woken up, we need to copy that stack back from the memory to where it belongs, where we need it for execution. So you can already see a small number of threads is no problem if it is similar to the number of cores that you have. But if you have a lot of threads, then the operating system needs to switch a lot, and this is very expensive. Looking at async execution, you can have multiple tasks on one thread, and in this example, to make it very simple, I just have one thread with two tasks on it. However, now we need to manage our tasks ourselves, because the operating system only manages the threads, but it cannot look what is inside the threads and what the individual tasks are. And this is exactly where an asynchronous runtime comes in, which manages and creates our tasks. So when the thread is active, the asynchronous runtime then decides which of the tasks should currently be executed. The execution of the tasks is then asynchronous, which means interweaved in this case, but on the single thread it can never be parallel. This is an example of how such a thread execution could look. We know that we have the await keyword that we already saw in code, and whenever task 1 runs up until some await keyword, the asynchronous runtime now knows that task 1 is probably waiting for something to happen. Therefore, control goes back to the runtime, and the runtime can decide to now execute task 2. Task 2 is then also run until some await keyword is hit, and control goes back to the async runtime. There is only one other task that can be run, and therefore task 1 is being executed if and only if whatever we've been waiting for on task 1 has actually finished. Like this, each task can contain multiple operations, and the individual operations are called futures. And when the async runtime makes progress on a certain future, it is also called driving a future to completion. Well, now that we know that we need an asynchronous runtime, let's just bring one of them, which is the most popular in Rust, into our dependencies. And this runtime is called Tokio. So we'll have the version of 1.36.0, which is the current one as of working right now. And we will make sure that we have the full features for it. Once we have all of this set up, we can now use a macro that is in the Tokio crate called Tokio main. And we will put this on top of our main function. And lo and behold, all the errors are now gone because this macro expands to something that will in fact take the async keyword away from the main function, but spawn an asynchronous runtime into the main function, and everything that we will execute here is then part of the asynchronous runtime. So let's try this out. I'll go run. And certainly we get in foo. So finally we have a working asynchronous program. The thing is, there is nothing really async about this program at all. All we did is slap some async and await onto our functions, but we don't have any functionality that has to wait for anything. So therefore, writing this program in sync would have been just as good as writing it in async. In order to actually make use of async execution, we will bring the request crate into our scope. What request is exactly what the name says actually. You can make HTTP requests and get the return values. The code that I have set up here has a function getStatus, which is async in nature and returns a result of either an HTTP status code, you know, the famous 404 page not found is one example, or it will just return some box of a dynamic error. What it does is it starts a timer, then it will launch the request get function to a certain URL that we will provide, which means it executes a HTTP get request. And this, of course, is a function that actually is asynchronous because we have to wait until the request returns some result back to us. So we have to await. We will bubble up any errors that happen here. And then once we have the result, we will only read the status code from it. After that, we will measure our duration and have a nice print statement of how long it took to fetch this URL and return our status code in an OK. The main function is also very simple. It is a Tokio main function as async. Then again, we measure the start time here. We get a first status from a first URL, do the same thing for a second URL, print the status out, and then we will just report the overall execution time. So I'm really hyped for this. Let's see what happens if we run it. Okay, both of the URLs got fetched. Actually, we got a status code of 200 OK for both of them, which is perfect. And looking at the timings, we have 83 milliseconds for the first fetch and 77 milliseconds for the second fetch. However, the overall execution time looks like everything just ran synchronously. Everything ran in order, right? This 161 milliseconds is basically both fetch times summed up. So even though we're again using async functionality, we are not running in concurrent. Something is still off here. Now let's dig into this and find out why we're not running concurrently. Well, the first thing that is supposedly async is getting status 1. The code execution runs to this line, then we await, which means we're actually executing this future. We're running into this function and we again have the get and await. And actually at this point, the async runtime, Tokio runtime, could drive another task to completion because this actually takes some time to wait. However, Tokio does not know about any other task being executed here because the second task that would be async has not even been started yet. So in this case, we're just waiting for the first URL to return to us. We get back, we print status 1, and only then will we execute the second async operation. Again, waiting for its completion here, and then putting out the status. So you see, even though we have all this fancy async await everywhere, there's no guarantee that we're actually doing something that has a performance increase over synchronous execution. Now, fortunately, Tokio has some very simple functionality to actually run multiple futures concurrently. This is done, for example, with the tokio.join macro. Tokio.join takes as an argument an arbitrary number of futures. And we don't need to await this because Tokio will take care of this. So we'll just put in the first one and the second one. And what we get back is then a tuple of all the results. So we'll take in status 1 and status 2 here for destructuring. And now let's clean up a bit here and of course just unwrap. Yeah, let's make this status 2 as well. Format this a bit nicer and try again. And lo and behold, the first fetch took 112 milliseconds, the second one took 81 milliseconds, but our overall execution time is only 130 milliseconds, which is around the time that our longest request took. So this time around, we were actually doing things in parallel. And running it multiple times actually yielded this result once, which is that the types and values was actually fetched before the index.html. So basically, it's up to chance which of the pages will respond quicker. However, the results will always be in the exact same order that you put your tasks in. So let's talk a bit more about how Tokio join works. Join, as I said, takes in an arbitrary number of futures, which you don't have to call await on because Tokio join will do it. It will then create individual tasks for each of your futures, which allows it to execute those concurrently, so in an async manner. Join will then wait until even the last task is finished to then execute the statements after the join. However, this is only one way of doing things concurrently with Tokio. You can be way more flexible than this. Let's say we'd have some function that we'll call heartbeat, okay? So this is an async function, heartbeat, and it takes in a number, and we'll just increase this number whenever the beat is being called. Let's say U32. In here, we will have a loop that will just print beating. And then we will do a sleep. However, we will have to be very careful here. We can't use thread sleep because then the whole thread that the heartbeat is running on will sleep, which will eventually deadlock our program if we're running on a single thread only. Instead, we will have to use an async function to sleep, which is in Tokio time sleep. And we will take in a duration from milliseconds, let's say 25. And because this is an async function, we will have to await it. And then in the end, we'll increase this counter by 1. Now what we want is this heartbeat to be running at all times, even while our fetch statements are being executed. So what we do is, we use Tokio spawn, and we'll put our heartbeat function in here, start with the number 0, and again, we don't have to await anything, we just put the future in here. You might notice that this is very, very similar to the thread spawn that we discussed in an earlier video. And that's exactly what it is, except for this time we're not spawning a thread, but we're spawning a Tokio task. Let us now run this, and we'll see that the heartbeat is beating all the time, every 25 milliseconds. And then around 179 milliseconds in, the first fetch is done, which totally makes sense because we have 8 heartbeats until here. Then we are beating the 9th time, and then the second fetch is also finished. So obviously this is running concurrently to our fetch requests on an individual task. And with Tokio spawn, you can now design your architecture of an asynchronous program, how you desire it, exactly the way you would be doing it with threads. Now, even though this is not a Tokio tutorial by any means, but rather an introduction to async programming in general, there is one more macro that I would like to highlight in Tokio, which is the select statement. The usage of the select statement is kind of similar to the join statement, where you would just put in some asynchronous functions or futures that need to be executed, and you would get the return type, even though this time you have to get the return type inside the brackets and not as a return value of the select statement. Also, for each of the futures, you can add some code that is being executed after the future has run. However, select works very differently from join. While join waits for all of the futures to have run, select basically erases these futures. So this code back here is only executed for the one future that finishes first. All the other futures or all the other concurrent tasks are being cancelled when the first future finished. So let's see this in action. And we see this time the first URL fetch was quicker, and it took 110 milliseconds to fetch this URL. However, the second one is nowhere to be seen because it was cancelled as the first one finished. So using select, join, and your manual Tokio spawns, you should be able to architect almost any program that you desire. Now there is one more thing I would like to introduce you to before we'll get to a wrap-up and discuss when to use async versus when to use threads. And this is channels. If you don't know what channels in Rust are, you're definitely missing out on a lot of the functionality you need for concurrency. So better watch my video on that. As a quick recap, channels are used to send data between concurrently running tasks. And if we do this for threads, then we would typically use the built-in MPSC channel from Rust. However, if we use those for concurrent programming, we're getting into a lot of problems with creating deadlocks. Therefore, Tokio has its own channels, which are async. In fact, they are also bounded, therefore you need to provide the maximum number of messages that can be in the pipeline. Other than that, syntactically, these channels work in the very same way that Rust channels do. We get a sender and a receiver when we create the channel. And in this case, I will spawn a thread that sends messages and therefore needs the sender side of this channel. The send message is very simple. We have a message number and then we just loop to send a string that just says hello from async and then the message number. And of course, because this is an async function, we need to await it and then unwrap. Following this, we'll just increase the message number and sleep with the Tokio time sleep for 1 second. On the other hand, on the receiving side, we have a function that is called receive messages, which is also async. It takes ownership of the receiver and has a while loop here in which the receiver is constantly being polled and awaited. Note that again we have the await here, which gives the Tokio runtime the possibility to execute other tasks while it is waiting to receive messages here. Running this program will yield the expected output. We have hello from async 1, 2, 3, 4, 5, again in 1 second intervals, which means that even on a single thread, we can run asynchronous as sender and a receiver of messages with the Tokio channels. Let us now see how Tokio manages all those tasks under the hood in an asynchronous runtime. We will do this in a massively simplified way, but I think this is very helpful to understanding the concept. Tokio works with something that is called an event loop. And this means that Tokio, of course, tracks all of the futures that have to be completed and will then cyclically ask them whether they can be completed or not. However, the Tokio runtime is very sophisticated and very smart. It doesn't do this with an endless loop, just polling all the futures. Hey, can you work? Hey, can you work? Hey, future number 3, can you do work? No. It's way smarter than that. Tokio actually knows why the individual futures or async functions have to wait. For example, future 1 might have to wait for some network I/O, future 2 waits for a timer to complete, and future 3 waits for file I/O. Now the runtime has some wrappers around those very fundamental basic operations like a timer or a network I/O, which means it knows exactly when of those operations has finished. And it does this via listeners. So for example, future 1 has had an await for a network I/O. Now it knows, okay, I have a listener to this network I/O, and whenever this listener returns to me that the network transaction has finished, I can then, whenever I have time, poll future 1 and try to drive it to completion. And yes, that was probably not necessary. One of the absolute basic and fundamental questions here is, when do I use async and when do I use threads? Well, threads are really good when you have CPU-bound tasks. So if you have tasks that are really heavy on computing, it doesn't make sense to wait for them in an asynchronous manner. You're just going to delay your computation, right? However, you also have to bear in mind that switching between threads is really expensive. So you shouldn't really overwhelm your computer with hundreds of tasks. A good rule of thumb is that if the number of tasks is not much larger than the number of your cores, you're in the right region. A very good example for this kind of behavior is scientific computing or computing in engineering. Think of computational fluid dynamics, finite element method, etc. All of these problems have in common that in the end, you will have a huge matrix that you will need to invert by some way of factorization or iteration or whatnot. And this can usually be parallelized very well. So what you would do is, for example, if you have 8 cores, you would split this matrix inversion problem into 8 subproblems. give every core its subproblem to work on, and whenever each individual subproblem is finished, you will reconstruct and you have your whole solution. So this is a very, very typical application for using threads. So when do we use async then? Async is really good at the things that threads are really bad at, which is perfect for us. Because async is very good at waiting for things. So if you have IO-bound tasks like waiting for a network connection to finish, waiting for a file write to finish, then you can of course do something else during this time. That's exactly what we saw with async execution. And because the async runtime can switch very, very efficiently between individual tasks, it is also possible to have a very large number of these tasks, even running on one thread. So having in the hundreds of async threads is not unheard of, actually. And the perfect example for this would be a web server. Because web servers, 99% of the time what they do is waiting. They're waiting for user requests, they're waiting to fetch data from some microservices, they wait for database access, they basically do nothing but wait, except for 1% of the time they actually do some computations. That's why web servers are your typical large-scale application of async code. Now, of course, you can have the best of both worlds, and this is exactly what Tokio's thread pool does. Under the hood, Tokio employs a worker pool that defaults to as many threads as you have cores. Tokio then goes on to manage your tasks onto the individual threads, so it will make sure that the tasks are evenly distributed across your threads. And Tokio will do this all on its own, without you even having to think about it. However, if you would like to set the number of threads to something different, you can do this with the main macro. Here we are in Tokio's documentation, and you can see that in the main macro, you can specify your flavor. Flavor would be multi-thread or current thread. And if you choose multi-threaded, you can specify the number of working threads. If you prefer to work on a single thread though, you would just specify current thread. Async Rust is a gift, and in conjunction with threads, it gives you the keys to writing extremely performant applications. However, when compared to synchronous code, things can quickly get more complex than most of us desire. Therefore, use it sparingly when it is required and resort to threads otherwise. As always, I hope these fundamental explanations about async and concurrency really helped you on the way to becoming a better Rust developer. I'll see you next time with Green Tea Coding.